Okay, today we will work on section 14.3. It is on partial derivatives. Definition. Let f of xy be a function of x and y. So x and y are the independent variables. Then the derivative of fxy with respect to x, keeping y constant, is denoted by usually we also call this partial derivative instead of just simply derivative. But at the same time, if you see from the context, this function is a function of two independent variables, then the derivative with respect to x must be the partial. Okay, now the notation. The first notation is f subscript x of xy. That's the first notation. The second notation is dou f of xy respect to dou x. So dou f dou x. Now, in Calc 1 and Calc 2, the derivative of the function usually denoted this, right? df dx, right? For example, okay. But when it comes to partial derivative, we use dou. The way to write it is like this: dou, not a d. Okay, dou f dou x, like that. Okay, now so for future reference, if you see this notation, then we know that function is a function of x only. If you see this notation, then that function is function of x and something else. Okay, now we have more. The thing is the notation for this partial derivative, we have a lot of that. Okay, another one is, suppose we have this function x and y denoted by z, for example, then we can also call this dou z of xy, dou z of xy, dou x. We can also write this as d subscript x of fxy. Of course, we can also write this as dx, capital D, of z xy. Okay, now if the context is clear, then we may just write f sub x or dou f dou x or dou c dou x or d sub x of f, d sub x of z. Okay, now if the context is clear, in context, then we can use those notation. Okay, the one we use a lot in our course are this type of notation. We use this type, most of the time. I mean, this type. Okay, this D, capital D notation usually being used in differential equations, or if you go even further, we use that in partial differential equation. That's the course after elementary differential equations. Okay, now then those are the notation for the partial derivative. Now, but how about the definition? N is given by f subscript x of xy is equal to the limit as h going to 0 of f x plus h comma y minus f x y over h. So it's very similar to our first derivative in calculus 1, okay? But because we have two variables right now, then you will see what we did is we are holding the y component constant, okay? The y component constant is hold or is held. I think it should be is held constant, okay? And x is varied, okay? The x is the one moving. Now from there you see that we do partial derivative with respect to x, which means only x is moving but the y is hold constant. Okay, now likewise, then the partial derivative of the function respect to y is limit h going to 0 of f x y plus h. So you see I hold the x constant right now. The y is the one varied over h. Okay. Now you will see basically when we have a function of x and y and you do partial derivative with respect to x, then we only see the x as the variable and the y as the constant or as a coefficient. Okay, for example, if we have fx equals to 2x to the fourth minus 5y squared plus 3x squared y cubed. Now then f sub x, which is the derivative of f respect to x, that will be 8x cubed, right? Now the second term becomes 0. Okay, and then the last term, when we do derivative with respect to x, that will be 6x y cubed. Okay, so we see the 3y cubed as the coefficient of x squared, you know, okay? So we keep that 3y cubed, and then the derivative of x squared becomes 2x. That's how we get that. Okay? And then if we do the derivative with respect to y, partial derivative with respect to y, from that function, then that will be negative 10y squared plus 9x squared y squared. Now I purposely give some space here so that you see which term I was working on. Okay, but of course when you do that on your paper, you don't need to give that space. Now, suppose then I ask what is f prime of 2 comma 1. Basically, you replace that function f sub x of xy, replace the x and y by those numbers. Okay, so this is 8 times 2 cube plus 6 times 2 times 1 cube. What is that? 6 times 8, 8 times 8 is 64 plus 12, that's 76. Now, and f sub y of 2 comma 1 will be negative 10 times 1 squared plus 9 times 2 squared times 1 squared. That's negative 10 plus 36, that's 26. Okay, I think to do the derivative is easy, especially if it is on polynomial, right? Later on, we will practice more on other type like sine, cosine, tangent, logarithm, and exponential. But I think what is more important is the interpretation of the first derivative with respect to x and the derivative with respect to y. Now, I would like you to follow me in sketching. Suppose we have that x, y, z coordinate system. And then I have a surface. So a function z equals to a function of xy. So let's say we have that surface. Okay, we have that surface. Now, what is the first derivative of a function? So let's say this is our z, the surface c equals to f of xy. Now, what does it mean to do the first derivative with respect to x? It means we are holding a y. Let's say this is the y. We are holding that cross section. We are holding this cross section here. Okay, so we fix the y. Okay, and at certain x, we are moving in the x direction by 1 unit. So this is our x comma y coordinate. You move in x direction 1 unit. Can you see that? I think instead of doing it there, let me change the position. Ouch. No, that's not what I want. I want a very small one. Let me do it here instead. What color should I use? Oh, I should use black color then. Okay, let's say I use this one here. Okay, so let's say this is my x comma y, right? Now then, the first derivative with respect to the partial derivative with respect to x means what? If you move in the x direction holding the y constant, then how far up or down will the value of your z? Okay, so I will take this part here. I will take this part here, that blue part here, this blue cross section, and I will graph that here. Okay, so let's say this is what we have at the on the ground. If we move 1 unit in the positive x direction, then what happened to the value of your z? Okay, this is your dose z. Okay, this is your dose z. Okay, now the curve may be like this. The curve may be like this. The curve may be like this. Maybe the curve, the cross section looks like that. But when we say the dou c dou x, right, it refers to how far the value will go down if we set the dou x to be 1. Okay, that's what it means. Okay, so because we set the dou x to be 1, then you can call this the dou z dou x then. Okay, basically if we move in the positive x direction, holding the y constant at that coordinate xy, how much the value of c will increase or decrease. Now what happens if we do dou c dou y? Let's see, suppose I do it, oops, not this color. Suppose I again start with XYZ coordinate system. And then let's say this is our surface. Let's say this is the surface. And that is the shadow of that surface on the XY plane. Now, the partial derivative of the function f respect to y will be done by holding the x constant. Let me do it here. We hold, let's say this is the x that I hold to be constant. That gives us this cross section, which honestly, every time I draw this part, it reminds me to my the slice bread. Right? If you have a bread and then you slice it, okay. Now, so you hold the x constant, right? And then at certain y, let's say at this y here, at this y here, we move 1 unit in positive y direction. We move 1 unit in the positive y direction. Now then, we wonder what happened, how much the z value will decrease. Okay, how much does z value will decrease? Let me use maybe this color, get larger. Pictorially, if I do the cross section on the right hand side here, let's say the graph looks like this, right? But then I want to observe that at that point I go 1 unit to the positive y direction. What happened to the change of that's too flat. Let me change that. What happened to the tangent there? Okay. So this will be my dou C while we set the dou X to be 1. If we set that to be 1, if we set that to be 1, then this dou C will take basically dou C dou Y. Okay, how far the function increases or decreases if we move in such direction. Okay, let me color this to grab your attention. Yeah, this way you know which cross section I'm talking about. Okay. By the way, before I move on, we will use this picture again in the next section or the next section. Okay, we'll refer to this again. So when I move on, I want you to notice what is this factor here. What is this factor here? What is that factor there? Okay, now that factor is factor in the x direction is 1 unit, in the y direction is 0 unit, and in the z direction is dou C dou X. Okay, or you can also say dou F dou X. Okay, while this factor here is 0 in the x direction, 1 in the y direction, and dou C dou Y in the z direction. Okay, we don't need it now, but it would be nice if we aware of that. Of course, we can also write this as 1, 0, f sub x, right? And this one here as 0, 1, f sub y. Okay, so I hope when you graph that, you know what we are talking about when we say a partial derivative respect to x, partial derivative respect to y. The next example. So we go back to our basically doing another practice of partial derivative. We say, let's say f sub fxy to be sine of x over x plus y. So what is dou f dou x, which is also f sub x, right? Okay. That is equal to the derivative of sine is cosine times the derivative of that blah respect to x, right? Now in Calc 1, we tend to do it this way. Okay, this notation here, the prime notation. Unfortunately, we could do that in Calc 1 because the derivative is clear respect to x. I mean, the function depends on only one variable. Right now, we cannot use this notation anymore. Okay, we cannot use that notation anymore because what? That function is multivariable, right? So instead of writing it that way, we can write times the chain dou x of x over x plus y. In other words, you have to write that notation now, the dou x. Okay, I do not accept the following notation, even though in some very old textbook it's okay. They write it this way. Basically, they say this is the u, and then you do the partial derivative with respect to x, like that. Okay, but I will not accept this kind of notation in my class. Okay, and I think I'd rather say that this notation, the use of this notation is way too early for you. Okay, if you go further, when you are more disciplined with how you write your work, I think it may be okay, but not for now. Not for now. Okay, so in my class, I still want you to write that dou x of whatever the blah, which if we do simplify, I will get cosine of x over x plus y times, then what is the derivative of this guy respect to x? I think I need to do quotient rule, huh? Okay, times, at the bottom I have x plus y squared. On the numerator I have x plus y minus x times 1. The derivative of x plus y respect to x will be just 1 plus 0. Right? Not 1 plus y. 1 plus 0. Which, if I cleaned up, I get cosine x over x plus y. And then the second factor, the x will cancel. We have only y. Y over x plus y squared. Okay, now how about dou f dou y? Then the derivative of sine blah respect to y will be cosine blah times the derivative respect to y of that blah, which is cosine of x over x plus y times x plus y squared on the denominator, right? And then the top will be, what is the derivative of x respect to y? That will be 0 minus x times the derivative of x plus y respect to y. That's 0 plus 1. Okay, which if we simplify, we will get negative of x over x plus y squared times cosine of x over x plus y. Okay, now of course, at this point, if you don't know chain rule, if you don't know quotient rule, you are beyond help in Calc 3. Okay, no, I'm not in position to teach you, but Thomas, you are my math teacher. I'm your math teacher for Calc 3, not for Calc 1. Okay, go back to your Calc 1 teacher if you forget how to do that. Of course, feel free to come to my office hour. I'm not that cold, but we need to separate what you're supposed to know, okay, and what I can help you with. Okay, I don't mind to help you, but that's not part of my job. Okay, I'm not the one teaching you Calc 1, Calc 2, or algebra and everything else. Okay, I can help you, remind you, I can tutor you, right? But don't then later on blame me for not able to make you understand, because that's not my job to start with. Implicit differentiation. Implicit differentiation is mainly used to differentiate a function or an equation in which the x and y are mixed. That's in Calc 1. Okay, in Calc 2, in Calc 3, then you may have an equation with a mixture of x and y and z, and it may not even define a function, okay, but we still need to find the partial derivative. So, for example, we have let x cubed plus y cubed plus z cubed plus 6xyz equals to 1. I don't think this is a function. Maybe not. Actually, it doesn't matter. Okay. And the question is find dou c dou x. Now, I need to make sure something. Notice that in this case, I cannot use dou f dou x. Why? Because we don't even know if z is a function of x and y. In other words, the reason we write it as an equation like this, okay, maybe because I'm just lazy, or the main reason maybe because we cannot rewrite that as c as a function of xy. Maybe not doable. Maybe z is not a function of xy. Okay, that's why then we use implicit differentiation. Okay, so implicit differentiation is actually a type of differentiation that we apply to something more than just a function, maybe an equation. Okay, so if you remember, way in Calc 1 we have x squared plus y squared equals to, let's say, 9. This is the equation of circle centered at origin with radius 3, right? Okay, and because it is not a function, you can see from the graph, then we cannot do y prime directly, right? Okay, because the y is not defined as a function of x, and it is not. Okay, but we still can do the partial derivative. When we do partial derivative at that time, if we want to do dy dx, right? If we want to find that, when we take the derivative of each term respect to x. Now, however, when we see y, we need to do the chain rule. And then from there, you solve for dy dx, right? But when we solve for dy dx, you notice that it is impossible for us to have dy dx as a simply function of x only. Okay, notice that dy dx here is still a function of x and y. Okay, so strangely, you have an equation whose derivative now, an equation whose dy dx now is a function, but that function is not a function of x only, it is a function of x and y. Okay, now that's one thing to say. Another thing to say is, do you believe that from there we actually also can do dx dy? Okay, beside dy dx, we can also do dx dy. So basically, you take the derivative of all the equation here, each term with respect to y. Okay, with respect to y. Now, in other words, you will see later on dou c dou x is one partial derivative we can have, but the partial derivative of x respect to z is totally fine also, because this equation does not say that z is a function of x. Okay, we just know that c is influenced by x, right? But x is also influenced by z. Okay, they actually influence each other. The change of x may change the z. The change of z may change the x. Okay, but for now, let's do dou c dou x first. And you will see later on that dou x dou z basically the reciprocal. Now, how do we do that? We do implicit differentiation with respect to implicit differentiation with respect to x. Okay. Now, notice that we want to find dou c dou x, right? So when we do the implicit differentiation with respect to x, okay, we consider z as a function of x, of course of y also, but y is not. In other words, we consider y as a constant or a coefficient of x. So when I do the derivative, x cubed becomes 3x squared. Remember, I do the derivative respect to y. I'm sorry, respect to x. Okay, so derivative of x cubed respect to x will be 3x squared. The derivative of y cubed respect to x will be 0. Okay, derivative of z cubed respect to x will be 3c squared dou c dou x plus. Okay, now 6xy is actually, you need to apply product rule because you have x there. Okay, you have z there. Now the y is just a coefficient, right? Okay, so I will apply product rule 6yc plus 6xy dou c dou x equals to 1. Do not use z prime, because c prime simply means you assume z is a function of x only, while in this case we do the derivative respect to x, okay, but in actuality z is also a function of y. Maybe I should say related to y. Okay, well, anyway, from here then you see I will isolate dou c dou x, so 3c squared plus 6xy dou c dou x equals to, I'm sorry, the derivative of 1 respect to x should be 0, equals to negative 3x squared minus 6yc. So dou c dou x will be negative 3x squared minus 6y z over 3c squared plus 6xy. We can simplify and reduce by 3, right? So this is equals to, and let me pull the negative out, negative of x squared plus 2yz over c squared plus 2xy. Okay, that's about implicit differentiation. The one you need to be careful is what is the variable that you need to differentiate against. Okay, so if you have z differentiated respect to x, then if you have x, differentiate that respect to x. If you have y, hold that constant. If you have z, you differentiate that respect to x, but don't forget chain rule. Okay, and of course, what if you have product rule thingy? Okay, next one on higher derivatives. Notation: f sub xx, that's easy. That's actually the second derivative of function respect to x, right? Denoted as dou squared f over dou x squared. Now, you may wonder why the second derivative notation looks like that, okay? And I hope then you understand why I emphasize the need of writing your notation properly, okay? It has a lot to do with your calc 1 though, but because right now it's more crucial because you will do the partial derivative with respect to different variables, okay? But suppose we have f sub x y. What does it mean? Does it mean we do the derivative with respect to y first and then respect to x? Or respect to x first and then y? And the answer is it's respect to x first and then y. Okay, so the actual notation is supposed to be f sub x sub y. That's why we write that f sub xy. Okay. Now, by the way, this sub y here is not multiplied by y, but subscript y. In other words, the derivative, the partial derivative f xy, right? The partial f respect to xy is actually the derivative of the function respect to x first, and then you do the derivative respect to y. That's what it looks like. Notice that if you write it using subscript notation, the reading is from left to right, but if you use dou notation, the reading is from right to left. Okay, now then if we try to write it shorter, then this can be written as dou squared f. Do you notice that on the numerator? This dou of dou f, right? That's dou squared f. On the denominator will be written as dou y dou x. It has to be in this direction. This means a second partial derivative of f with respect to x first, then y. Okay, now we didn't have that issue with the first notation here because it's with respect to x and then x anyway, right? So whichever you shuffle it, whichever way you juggle it, it will still be the same. Okay, but if you have two variables respect to x, y, that's the notation, and f subscript y x means you do the derivative of respect to y first, and then after that respect to x. Okay, now, but if we write the dou notation, it will be dou f dou y first, and then you apply the partial respect to x on it. Okay, now then we may write that second partial derivative as dou squared f dou x dou y. Okay, now this is the second partial derivative of the function f with respect to y first, then x. Okay, now that's for notation, but in you will see later on it's just applying how to apply that. That's actually quite simple. Okay, I will do examples later on, but let me just finish this up. The next theorem is a theorem that I will quote quite often in the long run, called Clairaut's theorem. Even though, strangely, our textbook does not mention this too much. It mentioned it here, but it seems like the author himself did not realize when we need to use this, when we can claim using this. Okay, but I will not prove this theorem, of course. This theorem is way too advanced. But at the same time, the reason I explained this theorem is to show you some strategy to describe something in math. Let's start with, let coordinate AB be an element of D, where D is a disk. Okay, so imagine if you have coordinate AB. Now this AB is inside a disk D. Okay, and this D is contained in the domain of the function of xy. So let's say this is the domain of that function. Okay, notice that, do you realize that this is actually a technique for them to say the point that we are talking about is not right at the boundary, but it has some space from the boundary. Why? Because that point is actually on the boundary. Then you cannot have a disk containing that point that is fully contained in the domain. So we are not talking about this kind of point. Okay, no, we are not talking about that kind of point. But can that point be very, very close to the boundary? Yes, yes. As long as it has some space such that you can fit a disk in there. Let's say that point is actually here. You see, it's very, very close, right? Okay, it's very, very close. But if we superzoom this, for example, which I actually do right now, okay, if you zoom this, notice that, oh yeah, I can actually fit a disk in there, right? Okay, do you see that? So we are talking about that kind of coordinate AB. So this AB is basically in the interior of the domain of that function. Okay. So Thomas, why don't you just say the interior? Because then I still need to explain what does interior mean, right? Okay. And suppose you have a domain that looks like a line and then a bulb like this, then can we use a point here? The answer is no, even though somebody may argue that's still the interior point of the domain, you know, okay, because the way we define interior maybe not, I'm not really sure anymore, it's a long time not using that. The word interior may means that if you take a circle, you can find something else in the domain. Then this point is in the interior, is inside the domain. It's not alone, it's not standing alone. Okay, but when we say if we define it this way, then we are guaranteed that you have a disk with any radius as long as it is a disk, okay, which is fully inside the domain. And I continue with this theorem. And let f sub xy and f sub yx be continuous on D. So not only on that coordinate, but it is continuous on D here, the whole thing here. Not only at that point, okay, but on this. But remember, this may be very, 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 very small. Okay, it's okay to be very small as long as it's not just a point. Now suppose this the mixed partial derivative with respect to x and y and respect to y and x are both continuous in that disk, then f sub xy at AB, which is contained in that disk, must be equals to f sub yx of AB as well. Okay, In other words, what this Clairaut's theorem says, that f sub xy at AB and f sub yx at AB may not be equal. So it does make a difference. What you did here and what you do here may not give you the same result if it is observed at a coordinate that is right at the boundary, that's first, or even if you can contain that coordinate in the disk, but either one of the mixed partial derivative is not continuous. Okay? In other words, if the continuity of the mixed derivative fails anywhere in that disk, then this equality is not guaranteed. Okay? Now, the nice thing is in this course, you will see that most of the case we are dealing with the mixed partial derivative. It's like I honestly only saw one question in our textbook, as far as I remember, whose mixed partial derivatives are not the same, and it happens to be the last question in this section. In other words, for the rest of this textbook, the mixed partial derivative will be continuous, and therefore they must be equal, because it satisfies the requirement of Clairaut's theorem. Okay. Now, don't hold my word though. Maybe in future it is possible that in the future we see something else. Okay, but as far as I remember, the last time I looked through the book quite deeply, the fourth or the fifth edition at that time, I found that only one question that only one functions in this textbook that does not satisfy the requirement of Clairaut's theorem. Okay, now the followings are not that important, but just give you some few introduction to partial differential equations that you may see in future. You definitely need to be in math major or in physics major, dynamical systems, or heat transfer, those things. Okay, an example of partial derivative, the use of partial derivative, for example, Laplace equation. Laplace equation is a function u sub x plus u sub y equals to 0. Okay, now if a function u respect to xy satisfies Laplace equations, then the function is called harmonic functions. Do I need to worry about this, Thomas? Nah, no. You don't need to worry about this. Our textbook has some examples, and I think I should say problems in the problem sets in which they want you to check if an equation is harmonic. Therefore, all you need to do is to show that it satisfies this equation. The second partial derivative with respect to x is the opposite of the second partial derivative with respect to y. Okay, now we also have wave equation, where the partial respect to the second partial respect to time t is equal to something squared of partial respect to x. Okay, but don't worry about this, because even if we have questions like that in your book and you want to try it, As far as I know, the question is always verify, show that it satisfies Laplace equation. Okay, now so the suggested homework from here, is from number 15 to 39, and then 41 to 71. You know what? Let me pick one question from our book. Let me pick one question from our book just to show that thing. Maybe I pick question number 76. Okay, let me mark this first so that when you look at your notes, you can easily locate the position of the suggested homework. I usually put it at the last, at the end of the notes, right? Okay, number 76. Determine whether each of the following function is the solution of Laplace equation. In other words, are this function u here harmonic functions? Okay, so notice that what you need to do is actually to show that it satisfies that Laplace equations. Okay, so u sub x will be 2x, u sub x will be 2, u sub y will be 2y, u sub y will be 2. Now, the thing is u sub x plus u sub y, is it equals to 0? I don't think so. Right? So function u, which is x squared plus y squared, does not satisfy Laplace equation and therefore is not harmonic. Now, don't ask me why they call that harmonic. I still don't understand like the harmonic series that you saw in Calc 2, like 1 plus 1/2 plus 1/3 plus 1/4. Honestly, I still don't know why they call that harmonic though. Okay, I believe, as I remember, it has something to do with waves or what's that? Signals, right? But why they end up calling that harmonic, I don't understand. So how about part B? U sub x is 2x, u sub xx is 2, u sub y is negative 2y, u sub y is negative 2. Yes, you can see u sub xx plus u sub y, is it equals to 0? 2 minus 2, that's equals to 0. So u equals to x squared minus y squared is harmonic. Okay, now that's for this section. I think they are quite clear about the notation. Of course, I can give you more examples, but you still have to practice yourself. Okay, you still have to practice yourself. That's for this one here. Right now it's 5:48. Let's come back at 6 o'clock. We'll continue with section 14.4, and this 14.4 here actually consists of only one main idea. But let me just at least write it down first. So section 14.4, which is on tangent planes and linear approximation. And you will see the continuation of tangent planes, which will give us linear approximation. The continuation of there will be a total differential. Okay, remember we did the partial derivative, right? Okay, in Calc 1 we have derivative of function f respect to x, for example. But in Calc 3 now we have partial derivative of function x f respect to x, right? Now those are the derivative. One of them derivative and the other one is partial derivative. Now then in Calc 1 we know the differential notation. Maybe I use this for example. If we have y equals to 3x squared, then the derivative of y respect to x will be 6x. No, that's the derivative notation. The differential notation will be 6y equals to 6 dy equals to 6x dx. That's the differential notation. Okay, now in Calc 3, suppose I have z equals to 3x squared y cubed, then dou c dou y, dou c dou x will be 6x y cubed. Okay, now of course we still can say the partial differential of c will be 6xy cubed dou x. But in our Calc 3, later on we will see dz, which is the total differential or simply just differential. But because z is a function of x and y, then the total differential of z will be affected by dou x and also dou y. Okay. So it has something to do with those. Okay, now let's go to the tangent planes for now. We start with a big picture. We start with a very big picture. I basically do the graph that we did earlier. No, not this. This time, let me try to make it bigger. So let's say this is the z-axis, the y-axis. No, not that one. And then the x-axis. And then I have a curve or a surface above that. Okay, and then remember the setup for partial derivative with respect to x. Let's say we take this slice here. Okay, let's say at this point. Okay, now, and then this factor here is tangent. This factor here is tangent to the surface at that point in the x direction. This factor here is 1, 0, f sub x, right? I wonder if you remember. And we also have at the same point, if we do the partial derivative with respect to y, in the interpretation we have earlier. We get let's say this is the factor. This is the factor 0, 1, f sub y. Now, notice that the surface, or I should say the plane that is spanned by these two factors, the plane that is spanned by these two factors here contains those two factors, of course, right? Okay, so the tangent plane contains that's 1, 0, f sub x and 0, 1, f sub y, right? So the tangent plane must be perpendicular to the normal factor, which is the cross product of those two. Remember, for us to find the equation of the tangent plane, we need to find a factor normal to it, right? Okay, so if we look back to that graph, let's say, let me use what color? Maybe this color here and make it thicker. So the normal factor will be this one maybe, right? That's the normal factor, okay? Which is given by ijk of 1, 0, f sub x, 0, 1, f sub y. And you will see this is negative f sub x, negative f sub y, comma 1. Okay? So, the equation of the plane tangent to z equals to fxy, surface C equals to fxy at, let's say, a comma b, fab is given by, okay, let's start. Okay, now that tangent plane must be normal to, the tangent plane is normal to this, right? Okay, so that plane must have an equation negative f sub x at AB times x plus, actually minus, f sub y at AB comma y plus z equals to d. Okay, and the d here, The C here is the you will see that if we reorganize this, we'll get Z equals to f sub x of AB times x plus f sub y of AB times y plus constant D, which we usually write the D first. Or you can also use C if you like. Okay, now how to find the D? Actually, another equation that you may remember from my section 12.5, I think. This is f sub negative f sub x a comma b times x minus a minus f sub y of ab times y minus b plus c minus fab equals to 0. Okay, which if you massage that, then you will get c equals to f of ab plus f sub x of ab times x minus a plus f sub y of ab times y minus b. If you want to call this a C, for example, if we call this a C, then our function will be z equals to c plus f sub x of x minus a. I ignore the a comma b for now, plus f sub y times y minus b. Now, some reminder in Calc 1. In Calc 1, we have this tangent line equation. The equation of tangent line is given by y equals to b plus f prime a times x minus a. If you have a curve, okay, then the tangent line at coordinate a comma b, this tangent line here is given by this equation, okay, where the b is the y value at a. So this coordinate here is a comma fa, which is a comma b. Okay, now mimic that right now, the similarity. Okay, the similarity. This is the value of the function at AB. Okay, this is the partial of f respect to x. This is the partial of f respect to y. Okay. Can you give an example, Thomas? Yeah, definitely. Let's say, for example, let me pick question from our book. Suppose I have question number 4. I hope this is reasonable. So let's find the equation of tangent line, a tangent plane of this surface at coordinate 2, 0, 2. Well, then we do z sub x equals to e to the xy plus xy e to the xy. Z sub y will be x squared e to the xy. So z sub x at 2, 0, right? You see, this is the x, this is the y, this is the z of xy, right, will be, this will be 1 plus 0, that's 1. Am I right? I try to do it visually. And then z sub y at 2, 0 will be 2. Oh no, 4, huh? So the equation of the tangent plane, will be given by z equals to the value at that point, which is 2, plus the partial derivative of the function respect to x at that point, which is 1, x minus 2, plus the partial derivative respect to y at that point, which is 4, y minus 0. So c equals to 2 plus x minus 2 plus 4y. The c equals to x plus 4y. Okay. You know what? Let's try to graph this. I don't know if our GeoGebra can actually do that magic, but let's give it a try. So we have z equals to x e to the xy. That's what it looks like. Okay. And then we want coordinate 2, 0, 2. So you see this point here? I think I don't like the color. I don't like the color. Should be like this then, huh? Yeah. Let me change the color. Change the color for this. Setting color, change it to something darker maybe, or brighter. This one. Okay, so we have that coordinate, right? Now, and then let's see the tangent plane. Z equals to x plus 4y. Is it that one? Let's see. Does it really tangent to it? Do you see that? Maybe I make this lighter, huh? I'll make this curve, the surface a lot lighter. Maybe we use this color. Okay. And the plane, let's use slightly darker. Okay, so you see at that coordinate A there, right? At that coordinate A, the pink one is the surface, z equals to x e to the xy, and the coordinate A 2, 0, 2. And then that plane, which is the green one, is tangent right at that point. Right at that point. Which way is the better point of view? Maybe this one here, huh? Yeah. No, not really. Yeah. You see, if we see it right from the sides of the plane, you see that plane is actually touch the point and also tangent to the surface at that point. Okay. So that's the tangent plane. Okay. Now next part. The next part, linear approximation, is basically the continuation from that tangent plane. If you remember what we learned in calculus 1, right after we learn the tangent line, the next topic after that is linear approximation. Okay, and the linear approximation at coordinate a of that function is given by whatever the value there plus f prime is approximated by f prime at a times x minus a. If you remember. Okay, in other words, when it comes to linear approximation now, it's continuation of our tangent plane. Equation of tangent plane is given by z equals to the value at AB, okay, plus the partial of f at respect to x at AB times x minus a plus the partial of the function at AB respect to y at times y minus b. Okay, now the linear approximation is basically replacing that value z by the L at a comma b. Okay, I think I prefer to say, yeah, yeah, it's like that. Okay, which is equal to the value at AB. You know what? I'm lazy, so let me just copy paste. Same thing, huh? Right? That's the nice thing with a computer. Okay. Now, therefore, suppose, continue. So, the value at a plus h, b plus k. So if you approximate this value from a and b, that's the same to the value at ab plus the partial derivative of f respect to x at that coordinate ab. So the starting reference point is ab multiplied by h. You see, in the h direction, you move in the h direction, right? This h is basically is supposed to be a plus h minus a from here. You replace the x by a plus h, right? Okay, minus a, you get the h only. Plus the partial of the function at ab respect to y times k. Okay, let's do more example. Let's see. Okay, let me use number 19 from our textbook. Okay, suppose we want to find out, use linear approximation to estimate f2 2.2 4.9. So f 2.2 4.9 with reference point 2,5 will be f 2,5 plus the partial derivative with respect to x at 2,5 times 2.2 minus 2 plus f sub y of at 2 comma 5 of 4.9 minus 5. Okay, so let me show you the no, this is too dark. Let me use yellow. So this guy goes here, this guy goes here, right? But the reference coordinate, let me use this one, 2 comma 5, 2 comma 5, this is the 2 comma 5, this is the 5. Okay, now then we plug in numbers. What is f 2 comma 5? That's 6 plus 1 times 0 0.2 plus negative 1 times negative 0 0.1. So this will be 6 plus 0 0.2 plus 0 0.1. That's 6.3. Okay, that's what we call linear approximation. Of course, we don't know what the function actually is, right? But as long as you don't move too much away from that 2 comma 5 and with the assumption that the function is continuous and differentiable, which means actually I need to say something about that. What does it mean if we have a multivariable function to be differentiable? Definition: the fxy is differentiable at coordinate AB if f sub x of xy, f sub y of xy exists near AB, maybe not at AB, but exists near AB, and continuous. At AB. Okay, basically the derivative, the partial derivative with respect to x and respect to y are both continuous and exist and continuous at AB. If we try to kind of like view this linear approximation, which basically we are using tangent plane, take a look on this picture here. Take a look on this picture. Suppose we have a curve, like a surface like this. Suppose we have a surface like this. At this point here, we have a tangent plane which is spanned by those two factors. Spanned by those two factors. Okay, now notice that those two factors actually form this parallelogram. Okay, now notice that this factor here, let me use what color? This one here. Yeah. This factor here is 1, 0, f sub x, right? And this factor here is 0, 1, f sub y. Now, the question is, what if we only go h unit in the x direction? Then this must be parallel to h0, h f sub x, right? Imagine if I multiply this factor here by h, okay? And imagine you go in the y direction by k units. So this must be parallel to 0 k f k f sub y. Okay, so notice that if I go only h unit in the x direction, let me make it thicker. If I go h unit in the x direction and then k units in the y direction, maybe I redraw it. So this is now my h comma 0 comma h f sub x, and this is my 0 k k f sub y, right? Then how far do you increase if you go in that way? Well, it's basically the sum of those two factors, right? If you think about it, how far we increase, that's basically the sum of those two factors. I want it thicker. Okay, so this factor here, this green factor here is h comma k comma h f sub x plus k f sub y. Okay, in other words, if you start from a comma b, from a comma b, move to in the direction of hk, right? Then the function f at ab will increase by h times f sub x of ab plus k times f sub y at ab. Let me try to sketch that again from slightly different point of view. So suppose this is the point, and it is increasing this way in the x direction and in this way in the y direction. So this is the plane. Okay, so it is increasing this way. And suppose on the ground, it actually looks like this. Like at this point, the height of that is this. You see that this is the increase. Okay, this part here, maybe I use a thicker one. This part here, this is h f sub x at ab plus k times f sub y at ab. Okay, where this is our h, this is the k, okay, and this is the f sub x, and this is the f sub y. Okay, now total differential, the next one. Oh, you know what, let's do a problem first. I think I did a problem already. Is there any other problem that I can work on? Yeah, no more. Or maybe I pick number 14. The question is find the linearization. So find the linearization. Linearization. Okay. Basically, we want to find the linear approximation of that function f at xy. Okay, at 3, 0. Let's see what is f30 first. F30 will be square root of 3 plus e to the 0, that's 1, that's equals to 2. Okay, now and then f sub x of xy will be, the derivative with respect to x is 1 over square root of, I think, 2 over x plus e to the 4y. Is it right? Okay, such that f sub x of 30, that is 1 over 2 times that square root, but that guy is the function, huh? That's times 2, so that's 1/4. F sub y of xy will be pretty much the same, but I do the derivative with respect to y on the top. I say 4 e to the 4y on the top over 2 square root of x plus e to the 4y. And then that will be at 30, that will be 4 over 4, which is 1. So the linearization will be of xy will be 2 plus 1/4 x minus 3 plus 1 times y minus 0. Okay, simplify to be 1/4 x plus y plus 5/4, huh? So 8 over 4 minus 3/4 is plus 5/4. That's the linearization. So as long as the xy is not too far from 3, 0, then we expect the value will not be too far from 2. In fact, it will be approximated by this tangent plane here. Okay, now finally, we can also write our tangent plane earlier. So we go to total differential now. Total differential. Notice that we have z equals to c plus f sub x, x minus a, plus f sub y, y minus b, right? This is the equation of tangent plane of z as a function of xy at a, b, c, where the c is basically f of a, b. Right? Now, I will move the c to the other side, and I will rewrite this a little bit. This is f sub x times x minus a plus f sub y times y minus b. Okay, now suppose suppose we replace x minus a as the difference in x direction, y minus be as the difference in the y direction, and therefore c minus c is the difference in the z direction, we get dc, which is the total differential, equals to partial respect to x times dx plus partial respect to y times dy. Okay, notice that this actually comes from linear approximation from tangent plane. Okay, now then how do we use this? We actually use that for the following situation. I will not go on with the functions anymore, but let's take a look on question number, let's say number 34. Number 34. Use the differential to estimate the amount of metal in a closed cylindrical can that is 10 centimeter high and 4 centimeter in diameter. If the metal on the top and the bottom is 0.1 centimeter thick and metal on the sides is 0.05 centimeter thick. Okay, so let's take a look first. So we have a closed cylindrical can. A closed cylindrical can. Okay, the height is 10 centimeter, and then the diameter is 4 centimeter, which means the radius is 2 centimeters. Okay, suppose I want to compute accurately the amount of metal needed to construct this can, then I basically need to find the volume of the exact solution. The exact solution. I need to find the volume of the lateral area. So the volume is equals to the area of the lateral area times the thickness on the sides, which is 0.05, plus 2 times the bottom area or the top area, 2 times because we have top and bottom, times 0.1, right? And the lateral area equals to the circumference 2 pi 2 times 10 times 0.05 plus 2 times the bottom area, 2 times pi r square times 0.1. So what will this be? 40 pi times 0.02. That's 2 pi plus, am I right? 10, 0.5. Yeah, 2 pi times, and this guy here will be 0.8 pi. So the total volume needed, the total amount of metal needed to construct that can is 2.8 pi centimeter cube. That's the exact solution. Okay, now another way to look at that is as follows. Suppose we look at the volume of that cylindrical can, which is with pi r square h, right? Okay, and then if we consider the change of the thickness as the change of the radius, the change of the height, then basically we get the change of the volume, right? So using differentials method, the change of the volume is the derivative of that volume respect to R times dr plus the change of the height, right? The derivative of that volume respect to height, which is pi r squared times dh, which is 2 pi r 10 0.05. That's the change of the radius, plus pi r squared times the change of the height. But the change of the height, notice that the change of the height is actually 0.1 on the bottom and 0.1 on the top, right? That's the change of the height. So it should be 0.2 here. Is it right? Okay. So you will see this is actually 2 pi plus 0.8 pi. Oh, we get the same answer, exactly the same answer. You can imagine the following. Suppose you have this can here, and then you want to paint it. And you want to paint that with the thickness 0.05 centimeter on the sides and the thickness of 0.1 centimeter on the top and bottom. Then how much paint you need? This is the amount of paint you need. Okay. And I think that's basically it. Let me see if we can do one more example just to kill the time. No more than. I think that's good enough. Yeah, basically we are saying that one way to see the amount of paint you need, or in this case the amount of metal you need, is to see how much the volume will change, to get that skin, to get that paint, to get that metal. Okay, and because the thickness is usually very small, very thin, right? The amount of paint you put on this cylindrical can, or the amount of metal you need to build that cylindrical can, if the thickness is small, then from there we can actually compute how much metal or how much paint is needed to paint it or to form that kind of cane. I remember one of my professor once made this comment before. It's about the sphere. It's about sphere. The volume of a sphere is 4/3 pi r cubed, right? That's the volume. And of course, they have their way to find the surface area of that sphere, right? I think instead of sphere, I should call that ball, not sphere. The volume of a ball is that, right? But how about if you want to find the surface area of that ball? Surface area. We know the surface area of a sphere is 4 pi r squared, which, if you think about it, imagine if you have that ball, okay, and then you paint it. It's basically change of volume, right? Okay, but it is a single variable. So the surface area, if you think about it, is basically the derivative of the volume respect to the radius. Do you see that? Okay. So the surface area of the sphere, because it is single variable, is the same to the derivative of the volume respect to the radius. And we can actually do the same thing for even if you have a box. Even if you have a box, you can find the surface area by doing the derivative. Okay, even though in case of box it will be more complicated, right? So if you have a box, rectangular box, the volume is length times width times height, right? So the surface area will be the derivative of the length. It's WHDL plus derivative with respect to W, LHDW plus derivative with respect to H will be LWDH. Okay, now the thing is, the change of the length, for example, here, it actually goes this way and this way. Okay, so this part here, this guy here, and this guy here is the change of the length. That's how we get 2 times. Okay, that's how we get 2 times. Which if you compare to the surface area of a box that we know from geometry, the surface area equals to 2 times width times height plus 2 times length times height plus 2 times length times width. Okay. Okay then, I think this is where I will stop for this 14.4. Let me see the suggested homework for you. As you can see, this section is not supposed to be on the hard side, supposed to be on the easy side instead. But of course, everything will be hard if you don't practice. Please do. Okay. Sometimes I feel like when I say that as if I said it in the negative way. No. I'm encouraging you. You want to improve. If you want to improve, you need to practice. Okay, as if I'm saying it's up to you, right? Okay, it's up to you, but do not say that you will be successful if you don't even do what you're supposed to do. Okay, yeah, I say this for you though. Okay then, this is it for today. On Monday when you come back, we will go on with 14.5, and I try to do a bit of 14.6. Okay, bye bye.
All right. Thank you.
Welcome.